Okay, in this presentation, we're going to look at some new concepts. Specifically, we're going to talk about momentum and energy. Now, those are the big overarching concepts, momentum and energy. But there are a lot of other concepts that we're going to talk about that are related to those ideas. For example, when you talk about momentum, there's a related concept called impulse, and those always go together. And so we'll see how impulse is something that creates a change in momentum. But if there's no impulse, then you have conservation of momentum, and we're going to talk about what that means. The next big concept that we're going to talk about is energy, which is related to another concept called work, and yet another concept called power. But let's think about energy and work because they are actually very closely related to one another. And so we'll talk about something called the work-energy theorem, which leads to the idea of conservation of energy, which, we have conservation of momentum, conservation of energy. This is really the big concept of these guys, that they are conserved, and we're going to talk about what that means. And then we're going to apply that idea of conservation of energy to some simple machines, and then we'll talk about some efficiency rules, and then finally we'll look at different sources of energy, which is going to be important. So we can start with a simple definition. Momentum is called inertia in motion, but really what it is it's defined as the product of mass and velocity. And remember from your math classes that product means multiply. So in momentum, if you want to write it as an equation, you would say that the momentum is equal to mv, where m is the mass and v is the velocity. And so the mass times velocity, that is what momentum is. So if I had a object that was moving at 5 meters per second and it had a mass of 5 kilograms, I would simply multiply those together and I would say that the momentum would be equal to 5 kilograms, that's the mass, times 5 meters per second. That would be the velocity, and that would be equal to 5 times 5, kilograms meters per second. And that's the units. You just multiply kilograms times meters per second, and that gives you the momentum. So that's the momentum. And that's the basic definition, just mass times velocity. Now, if you remember, we talked about velocity being something for which the direction was important. And if you don't care about the direction, then you can say that the momentum is going to be just the mass times the speed. But again, the symbol would be momentum is mass times v. So the direction can be important with momentum, but if you just want to know the amount of momentum, you just say the mass times the speed. Okay, so we're continuing on with our idea about momentum, and remember momentum is just m, which is the mass, times v, which is the velocity. And so if you have either a big mass or a big velocity, that can lead to a high momentum, a big momentum. If you have both a high mass and a high velocity, that's going to make the momentum even bigger, a higher momentum. But if the mass is low or if the velocity is low, that's going to make the momentum smaller and will lead to a lower momentum. And if both the mass and both the velocity are low, then that gives you the lowest possible momentum that you can get. So here is a question to check your understanding of this concept. When the speed of an object is doubled, what happens to its momentum? Now remember, momentum is defined as mass times velocity, or mass times speed. So if the speed is doubled, that means it goes up by a factor of 2. What happens to this whole thing? Well, if I multiply one thing by 2, that's the same as multiplying everything by 2. And so your options are the momentum remains unchanged in accord with the conservation of momentum, it doubles, it quadruples, or it decreases. Now let's think about this. What we've done is we've taken the velocity and we've multiplied it by 2 times. We've doubled the v. So what's that going to do to the whole thing? It's just going to double it. And so the answer is the momentum doubles. Okay, the next concept we want to talk about is something called impulse. And impulse is related to momentum. Now, impulse is defined as the product, again, that means multiply, of force and contact time. So if you push something, so you might push a box, for example, and so I've got a box, and I push on it with some force, and the box is going to slide across the floor. Well, if I push for 5 seconds or if I push for 10 seconds, there's a difference. And so what the impulse is it's defined as the force times the time. And so F times T, force times time, that's how you calculate the impulse. Now what that means practically, if you have a big force that's exerted for a long time, that's going to give you a big impulse. But if you take that same force and exert it only for a short time, that means you're going to get a smaller impulse because you're multiplying by a smaller number. So let's check our understanding. When the force that produces an impulse acts for twice as much time, the impulse is not changed, increased by 2 times, increased by 4 times, or decreased by half. Now, let's remember the impulse is defined as the force times the time. And so if I double the time, so I make that goes up by 2 times as much, the whole thing doubles. And so that's the answer. It is increased by 2 times. It doubles. And so that is basically the answer to the question. Now, I said earlier that impulse and momentum are related. What we want to see now is how are they related? What is the connection between impulse and momentum? And the answer to that is a change in momentum is equal to the impulse applied to it. So if I have an object and let's say I've got my box again, so I've got my box and I push with some force for some time t, what's going to happen is that box is going to accelerate. Remember what accelerate means. Accelerate means it's going to change its velocity. In this case, it would speed up. It would be going faster here. And so the mass times velocity is going to change because the velocity is getting bigger. When you apply a force to something, it accelerates and it's going to change its speed. In this case, it's going to speed up. So this thing's going to get bigger. And how much bigger does it get? Well, it turns out that the amount that mv changes is equal to that impulse, the force that you apply, times the amount of time you apply it for. And so if I apply it for 2 seconds, it might move to here. If I apply it for 4 seconds, it might move to over here somewhere. It's going to continue accelerating all this time that the force is applied, so it'll be going faster and faster and faster. So you would get a bigger change in velocity for 2 seconds than you would for 4 seconds. And so how much velocity change you get, or rather how much momentum change, mass times velocity, that is equal to the impulse. Now, this little triangle here, I think we've talked about that before. That's the little Greek symbol delta, and that means change in. So when you see delta times mv, that means the change in mv, which is, of course, the change in momentum. So here are some ways that momentum can change. For example, if we want to increase the momentum, we can apply a great force for a long time, and that'll give us a big change in momentum. A golfer follows through while teeing off. And so if you have a golf ball, and you want to hit it with the edge of your golf club, well, you don't want to just smack it and send the golf ball sending with just a short little smack. You want to hit the ball and make contact, and the whole golf club swings, and you want to maintain contact with the ball during that whole swing, because then the force of the club is being exerted over a very long time, and so that means that the ball is going to get a bigger change in momentum, mv. And so the longer that the swing is in contact, the bigger the change in velocity, and so it'll leave the club faster, and that means your golf ball will travel further. Another example would be the long barrels of long-range cannons. And so you have a cannon with a barrel that's very, very long, and the bullet is going to be going faster and faster down the length of the tube. what's actually happening is the gunpowder explodes back here and it causes gases to push the bullet forward down the barrel, and it can go faster and faster down the barrel. And when it leaves the barrel, it's going to be no longer accelerated because those gases will flow out of the barrel and they won't be pushing the cannonball or whatever it is anymore. So that is why the longer barrels are useful, because they can actually make the ball go faster when it launches, and then it'll do more damage when it hits whatever it's going to hit. Okay, so here is actually kind of a tricky question. So a cannonball shot from a cannon with a long barrel will emerge with greater speed. Why is that? It's because the cannonball receives a greater A, average force, B, impulse, C, both of the above, or D, neither of the above. And the answer is actually impulse. It receives a bigger impulse. Because remember, the impulse, Ft, that's equal to the change in momentum, mv. And so the mass doesn't really change. So what we're really talking about is the change in velocity here. And so by having the longer barrel, you get a bigger change in velocity because you have a bigger impulse. The force is the same. The force provided by those expanding gases is going to be the same. But the longer barrel means that those gases are pushing on that cannonball for a longer time. And this whole thing, the whole impulse gets bigger. And that means the whole change in momentum gets bigger. And the cannonball exits the barrel going faster than it would for a shorter barrel. Now, here's another case of momentum change, one where momentum is decreasing. And so decreasing the momentum over a longer time means that the force is smaller. So here is an example. If you dive into a haystack, the haystack is going to slow you down until you stop. But if you dive head first into a brick wall, wow, you just smack against that brick wall and you stop immediately. So the amount of time it takes you to stop from the brick wall is much shorter. Now, you're going into the momentum, or I should say, you're going into the object with a certain amount of momentum. So you're some object, you've got a mass, you've got a velocity, and then you hit something that's going to make you stop. And so the two options are you hit a haystack or you hit a brick wall. And so if you hit it, so the amount of momentum change is the same. So it's going to require the same amount of momentum change to stop you, whether it's the haystack or the brick wall. And so F times T, that's got to be the same. So what's different? The brick wall is going to stop you immediately. The time is going to be very, very small. And so to give you the total amount of impulse you need, that means that the force has to be very, very big. Now, if we're diving into the haystack will stop you over a much bigger time, and that means the force is going to be smaller. Now, which would you rather be hit with, a bigger force or a smaller force? Obviously, most people would want to be hit with the smaller force. That's why diving into a haystack is preferable to diving into a brick wall, because a brick wall is going to stop you over such a small time. The amount of force needed to stop you is going to be a lot bigger. But since the haystack spreads the time out, that means the force is going to be much smaller. Another big example of this, kind of like a haystack, is the airbag in a car. The airbag in a car acts like a cushion, but it slows down the amount of time it takes you to stop. So if you were to slam into your steering wheel, if you had a wreck and it threw you forward into your steering wheel and the steering wheel stops you, that steering wheel is really hard and rigid, so it would stop you very fast. And that would mean that the force it used to stop you would be very, very high. But the airbag, it slows down how long it takes you to stop, because it's, the airbag basically is this big cushion and you hit it and it deflates and it compresses, and so you stop over a much longer time than just hitting the steering wheel by itself. And so what that means is that the force applied to your face is much less. That's why an airbag can save your life, because it can mean that the force is vastly smaller than it would be just hitting the steering wheel column. Just that hard, rigid steering wheel would smash your face good. So the airbag is a very useful safety invention. So just to recap, here's the idea. I've got some mass times velocity. I hit my haystack, and so the haystack applies a force times a time that has to equal the mass times velocity. Now, since the time is really big, the force can be small. But when that same truck hits a brick wall, the time it takes to stop is much smaller, and so the force has to be really bigger. Here are some more examples of this concept. When you jump, if you were to jump off, if you were in a building that was on fire and you jumped out of the window of a second-story room onto the ground below, when you hit the ground, you would want to bend your knees. You wouldn't want to keep your legs stiff. And the reason for that, when you bend your knees, when you make contact with the ground, it makes it longer for you to stop. So you hit the ground with your feet, but you're still moving, and so you bend your feet as you slow down. And that, I'm sorry, you don't bend your feet. You bend your knees as you slow down. And that means that the amount of time it takes you to come to a stop is much bigger. Whereas if you just kept your legs stiff, you would stop really, really fast. The force would be bigger, and you might actually break your knees if you tried to do that. And so that's why you bend your knees when you jump and when you land from a jump, because that increases the amount of time it takes for you to come to a stop. It increases the amount of time it takes you to change your momentum, so that means the amount of force is smaller. Same thing with boxing. If you get punched in the face, you want to roll with the punch. You want to kind of move backwards with the punch to make it take longer for that punch to be delivered to you. Whereas if you just, stand rigid and take it, the force of that punch is going to be much, much bigger. For the same reason, because the difference is how long it takes the punch to be delivered to you. And of course, a smaller time means a bigger force, and vice versa. So you want to make the force as small as possible, so you roll with the punch so that you diffuse it and let the time increase so that the force gets smaller. Okay, so we have one of these little quizzes to check our understanding of this concept, and it says, a fast-moving car hitting a haystack or hitting a cement wall will produce vastly different results. Both experience which of the following? The same change in momentum, the same impulse, the same force, or both A and B? And the answer is, dun dun dun, both A and B. So what does that mean? That means the same change in momentum and the same impulse. Now let's think about how we can reason that out, because we know that the car has some mass times velocity that it's starting with, and then it goes and then it hits something, the wall or the haystack, and then it comes to a stop. And so here the velocity is equal to 0. And actually that means that the mass times velocity is equal to 0. And that's going to be true for whatever the starting momentum is. It's going to be the same regardless of whether you hit the haystack or the brick wall. You're going to have the same starting momentum and the same final momentum. So that means the change in momentum is going to be the same. And we know that the change in momentum is equal to the impulse. So if the change in momentum is the same, the impulse has to be the same. We know that Ft, that's the impulse, equals the change in momentum, delta mv. And so if the momentum change is the same, that means the impulse, F times t, must be the same. Now, we already talked about in the previous slides, the time is what's different, and that means the force is going to change. And so the same force is not what they're going to experience, and so that means both A and B is the answer. Now here's another question. A dish falls onto the ground. Will the change in momentum be less if it lands on a carpet or if it lands on a hardwood floor? And there's an admonition here, be careful. And the answer is the change in momentum is going to be the same. And it's the same idea as last time. So we have this plate. It's got some mass times velocity, some momentum that it's falling with, and then it hits the ground and the ground stops it. Maybe it breaks apart, maybe it stays whole, but it stops at the ground and so its momentum goes to 0. Regardless of whether the plate lands on carpet or on hard floor, that is going to be the same change in momentum. The momentum it started with is going to end up with mv equal to 0 because the velocity is 0. And so it's going to be the same change in momentum regardless of what momentum it started with. Now, what will be different is the force applied to the plate and the amount of time it takes to land. If it lands on a hard floor, it's going to stop very abruptly. But if it lands on carpet, the part of the carpet that's soft is going to cushion it and compress and make it take a lot longer for the plate to come to stopping. And so the carpet will give you a bigger amount of time for the plate to stop, and that means a much smaller amount of force pushing on the plate. That's why the plate's more likely to break if it lands on a hard floor than if it lands on a carpet, because the force is bigger on the hard floor. Now, the next thing that we want to talk about is the idea of something called conservation of momentum. And in every case, the momentum of a system cannot change unless it's acted on by an external force. In other words, there has to be some force to give you an impulse that will change your momentum. If there's no force, there's no impulse. And if there's no impulse, there's no change in momentum. And so a system will have the same momentum both before and after any interaction if there are no external forces that change the momentum. And when that happens, we say that the total momentum does not change, it is conserved. And so here's the rule, and this rule is called the law of conservation of momentum. The law of conservation of momentum. It says, in the absence of an external force, the momentum of a system remains unchanged. Period. It doesn't change. So in equation form, we have the total momentum before equals the total momentum after. Now, very often when you see momentum written as an equation, it's written by the letter P. It's indicated by the letter P. So P is equal to mass times velocity, and that is the momentum. And so I don't know why they use P, but they just do. And so you can say that the momentum, or P before, is equal to the momentum after. And that's not the momentum necessarily of a particular part of the system, but the momentum of all the parts of the system added together. That is going to be a constant value. So here is another area where momentum is conserved, and that's in collisions. When two things, if something is moving or two things are moving towards one another and they smack together, they have a collision. And in that collision, the forces are what are called internal forces. It's like Newton's third law. The two things are pushing against each other. So those are called internal forces, and they don't change the momentum. In order to change the momentum of something, you have to have an external force. And so that would be, someone out here pushing or something. That would be an external force. But without that, the momentum of the object is going to be only interacting with what we call internal forces. And so it takes external forces to change the momentum. Now, there are different types of collisions. And so the two different types of collisions are called elastic collisions and inelastic collisions. But in any kind of collision, the momentum is going to be conserved. And this statement here is the most important part of this slide, because it tells you that in any kind of collision, the net momentum before the collision is equal to the net momentum after the collision. So what that means is I've got these two things up here, and they're going to each other, and they're going to smash together. They're going to collide. The momentum of this guy, that means the mass times the velocity of this guy, plus the mass times the velocity of that guy, they're equal to each other before the collision and after the collision. So let's look at what's called an elastic collision. And an elastic collision is defined as a collision whereupon objects collide without permanent deformation. That means they don't get smashed up, or the generation of heat. So basically, you can think of elastic balls bouncing as being a good approximation of an elastic collision. And here we see, this slide looks a little complicated, but it's actually not too bad. Let's just go through, there's three cases here. There's case A, there's case B, and case C. And so in case A, we've got the green ball is moving towards the yellow ball, and you can see the blue arrow showing you that it's moving. This guy doesn't have a blue arrow, and so it's not moving. It's just sitting there. And so what happens, now we're going to assume that these two balls are the same mass. So think of like two pool balls. Like maybe this could be the cue ball, and this could be a regular pool ball. And so this ball comes in, it hits it, and then what happens is the green ball stops dead in its tracks, but the yellow ball moves forward with the velocity that the green ball had. And so basically, in this kind of collision, the green ball transfers its momentum to the yellow ball. So this guy's got no velocity and no momentum. This guy's got a certain amount of momentum. They collide, and then the green ball is the one that doesn't have any momentum because it stops, but the yellow ball stole its momentum, and it's moving forward. Now, the law of conservation of momentum tells us that the amount of momentum that this guy has is the same amount of momentum that that guy had before the collision. So the momentum after the collision equals the momentum before the collision. And you guys may have seen this in pool where the cue ball strikes a ball and the cue ball just stops dead in its tracks and the other ball goes on. That can be explained by conservation of momentum. Now, that actually will only work if these guys have the same mass. But that is the basic case, case A. Now, in case B, you can see both the balls have an initial arrow, so they're both going in the same, they're both going with velocities, but they're going in opposite directions. So they're approaching each other. They collide, and then they bounce apart. So before the collision, they have a certain amount of momentum. They collide, and then after the collision, they have a certain amount of momentum. Now, one thing that I want to caution you, remember, when the arrow is pointing backwards, like this guy and that guy, we say that those are negative quantities. And so the green one here would be positive, and the yellow one would be negative. They bang together, they transfer momentum, and then after they transfer momentum, the green one is now moving in the negative direction and the yellow one is moving in the positive direction. But so the green one had a positive momentum, it now has a negative momentum. The yellow one started with a negative momentum, it now has a positive momentum, but the total momentum of the two added together is going to add up to be the same. How do I know that? Because that's the rule. The momentum of the whole system before has to equal the momentum of the whole system after. And then part C, we can see they're actually both going in the same direction, but notice the yellow one has a smaller arrow, meaning it's going slower. That means the green one's going to catch up. And then what happens is they collide, and the yellow one speeds up and the green one slows down. But again, the total momentum of this guy plus this guy has to be the total momentum of the two added together before. The momentum before the collision has to equal the momentum after the collision. That's the rule. Okay, in the previous slide, we were looking at what are called elastic collisions. Now we want to look at what are called inelastic collisions. And so this is an inelastic collision here. Now, when we think about an inelastic collision, the most common case of that is when things stick together. And when things become tangled together or coupled together, that process generates heat and causes the system to lose energy. And that's really the difference between an inelastic collision and an elastic collision. The elastic collision does not lose energy. The inelastic collision loses energy. But for the most part, what you can think about it as the inelastic collision is where the things stick together during the collision. So here we have an example of two railway cars that are traveling down the track, and we have this orange car which is moving with a velocity of 10, and this green car which is initially at rest. The orange car collides with the green car, so they collide and they stick together, they latch together, and then they go off. And it says here that they're going to go off together with a velocity of 5. So the orange one started with 10, the green one started with 0. They collide together, and they go off together half as fast. Now, of course, that's assuming that the orange car and the green car have the same mass. So let's see how that works. The total mass before the collision is going to be the mass of the orange car times its velocity plus the mass of the green car times the velocity is 0. And of course, anything multiplied by 0 cancels out. And so we've just got the mass times velocity, or 10 times the mass times 10. That's going to be the total momentum of both cars together, the 10 times m plus the 0 times m. That gives me 10 times m as my total momentum. They collide and stick together, but during that collision, the total momentum doesn't change. And so what we have is now they've joined together, so they've got 2 times the mass. They've doubled the mass. But the mass times the velocity has to give you m times 10, because that's what you started with. And so that means that the velocity now has to be 5, because 2 times 5 gives you 10, 10 times m gives you 10 times m, which is what it has to be. The long and short of it is this. The momentum after the collision, the total momentum of all the cars after the collision has to be the total momentum of all the cars before the collision. The momentum has to be the same. So let's check our understanding of this. Freight car A is moving towards an identical freight car B that is at rest. When they collide, both cars couple together. Compared to the initial speed of A, the speed of the coupled cars is going to be the same, half, twice, or none of the above. And I think from what we just talked about, hopefully you said half, because that's what it's going to be. And so if that doesn't make sense, back it up a little bit and watch the previous slide again, but I think that hopefully that will be clear.